Welcome guys, today I'm going to be solving a challenging Olympiad geometry problem. We're given a convex pentagon with 5 triangles of equal area inside of it. Triangle ABC, BCD, CDE, and so on in a circle 5 times. And their area is all equal to 1. And the problem is to find the area of the entire pentagon. So follow through with me for the solution and you'll be surprised how much you can derive with such minimal information. Okay, first we're going to recall actually a theorem that states when we have two parallel lines, let's say with points C and D and points A and B, and we connect two triangles so that share base AB, we have that the area of ABC is equal to the area of ABD. This is a theorem and the converse is also true for it. So basically if two triangles share the same base, then they must have parallel lines at the top of their top vertex. This makes sense. We can drop the same height and it's easily proved. So once you apply this to the case what is here, we know that the area of triangle CDE is equal to the area of triangle ADE. That means the lines AC and ED have to be parallel. Okay, here we have that area of CDE is equal to the area of AED. Therefore, AC must be parallel to ED. All right, and by similar logic, we can also conclude that there's also four other pairs, 5 in total, of such parallel lines. These lines end to the edge of the regular pentagon, right? Okay, going to write it down quickly. We will need AB parallel to EC in this problem, and AD parallel to BC. So yeah, BC parallel to AD. Okay, now it must make sense that we can easily spot some angles in here. So I'm going to take out a different colored marker and show you. Because there are parallel lines, we know that alternate interior angles must be congruent. So we have angle such as ADE is congruent to angle DAC right here. Because again, the parallel lines, we showed that they are parallel. And if we look in the trapezoid BCDA, we know that angle BCA must be congruent to CAD. And then we also have another pair of angles which starts again here with CED, then ACE, and BAC right here. Okay, and that is all simply by alternate interior. I'm going to quickly write it all down. All right, and here you must see something very interesting. Recall by the reflexive property that AC is congruent to CA, the reflexive property. And look at this. Apparently it doesn't seem like so in this picture, but triangle ABC should be congruent to COA, which is pretty cool. We have triangle ABC is congruent, not just similar, but congruent to COA by the angle side angle rule. And therefore we know that the area of COA is equal to the area of ABC. And that is equal to 1. Because here we have area of ABC is equal to 1. And that is given to us. And that is pretty cool. And now if we know that this triangle in the middle is equal to 1, we can make a very interesting equation that we can later solve to find the area of the whole pentagon. Watch this. All right, let's have the area of AOE equal to y and the area of the small triangle ODE equal to x. You'll see why in a moment. Let the area of AOE equal y, and the area of ODE equal to x. Because now we're going to use the particle postulate to express the entire area of the pentagon with this. Notice that the area of the pentagon ABCDE, we can look at it in two different ways, which will both be important for finding a system to find these values of y and x. We can look at it as the sum of the areas ABC plus COA, which we proved is congruent to ABC, plus another triangle we know CDE, and plus the segment AOE. Let's write it all down. Of ABC plus COA plus CDE plus Y, which we have AOE. Okay? That's equal to, we know each of these three triangles areas is 1, so that's equal to 3 plus Y. Okay? Also, we know that the area of the pentagon, we can express it similarly using x, which is this small triangle right here. It's again equal to the area of ABC plus, it's going to be COA, the middle one, plus CDE, but then we're going to have plus ADE, and it's going to be minus x. Make sure you see why. We have CDE and ADE. They share an intersection. They intersect with this OED right here. So if we subtract, so basically we're adding twice of this triangle, and we have to subtract 1 to have us left with one of these. And that is going to equal to 4 minus x. Hopefully this makes sense. And we can then, by transitivity, say 3 plus y is equal to 4 minus x. But that doesn't really help us. Again, we need one more equation to finish this system. And I mean, the first thought is obviously saying that y plus x is equal to 1, because it is. But try it out, and you'll get an empty set of solutions. It does not help. For this, you have to recall one final theorem, which I'm going to draw out here. If you have, again, two sets, if you have one pair of parallel lines, right here, it's commonly seen with trapezoids, and we have their diagonals intersecting at O, then we know that the theorem, the area of AOB times, the area of AOB times the area of DOC is equal to the area of AOD times the area of BOC. And this is often called actually the butterfly theorem. Okay? Because we're kind of like crossing it over, like a butterfly, like wings, not sure why. Okay? Going to shade it in. It's going to be these two times the other two. That is a theorem. And as you can probably guess, in our case, where we have the parallel lines AC and ED, we can say the same thing. We have this is X, this is Y. Both of COD and AOE should be equal, and therefore we get also that X times 1, AOC is 1, is equal to Y times itself squared. And that basically could be our solution. From then we just solve a system and we get the answer. We just substitute in y squared for here, and we get a nice quadratic, which would be y squared plus y minus y plus y minus 1 is equal to 0. Seems like, and I'll spare you the calculations. The solution is y is equal to root 5 over 2 minus 1/2. I know you can solve a quadratic from here. And thus, once we add 3 to this, we get that the final area of the pentagon is equal to 5 halves plus root 5 halves. And that is, in fact, the answer. So, yeah, it's a very interesting problem with how much minimal limited information we can find such an interesting result. And that is it. Thank you for watching.